Welcome to Ask and Learn.
We are given the equilibrium constant K for the isomerization of glucose 6-phosphate into fructose 6-phosphate. And we want to use this information to help us solve out the appropriate values that are required for parts A through D of this problem. And these two equations will be useful for us as we do that. In part A, we want to find the change in Gibbs free energy at standard conditions using the equilibrium constant and a temperature of 298 Kelvin. So therefore, we need to use the equation on the top to help us do that. So that would be equal to negative R, which is 8.314 joules per mole times Kelvin, times the temperature of 298 Kelvin, times the natural log of that equilibrium K constant, which is given as 0.510. When we work through the math, we should get a final answer in part A for the change in Gibbs free energy at standard conditions for this isomerization reaction at 298 Kelvin to be 1.67 times 10 to the third. And when we cancel off units of Kelvin, we're left with final units of joules per mole. So that is the answer for part A. In part B, we need to find delta G, and we are told that the ratio of fructose 6-phosphate to glucose 6-phosphate is 10 to 1. So the concentration of fructose 6-phosphate to the concentration of glucose 6-phosphate equals 10. We write out the equilibrium constant expression. We see that we need the concentration of the product, which is F6P, divided by the concentration of the reactant, which is G6P. And when K is equal to this value, then we are at equilibrium. But in part B, it's not equal to that value, it's equal to 10. So that means that represents Q, the reaction quotient in this case. And we need to find delta G at non-standard conditions in part B, and we are given Q. So we need to use that equation this time. So delta G equals delta G at standard conditions, which is what we just solved for in part A, because this symbol denotes standard conditions, but now we have moved to non-standard conditions since we have a value that for the equilibrium constant that deviates from the true value. So now we have a reaction quotient, Q, instead of K. So 1.67 times 10 to the third joules per mole, again, was that delta G value at standard conditions. Now we add RT ln of Q. R is 8.314 joules per mole times Kelvin times T, 298 Kelvin, times the ln of Q, which we are told in this part B that is equal to 10. And now when we work through the math, you get delta G equals 7.37 times 10 to the third. That again will have units of joules per mole after we cancel out units of Kelvin. And now in part C, we are essentially doing the same thing as part B. We are explicitly given a value for Q. It's not written in a ratio of the concentrations of the product to the reactant. So we use that value of Q in the same equation using the delta G at standard conditions from part A again, 1.67 times 10 to the third joules per mole plus RT ln of K, 8.314 joules per mole Kelvin times T, 298K, times the natural log of Q, and in part C, we are told that Q equals 0.100. We plug in those numbers into this equation and get delta G at non-standard conditions in part C equals negative 4.04 times 10 to the third. And again, it has units of joules per mole. And in part D, this time we are told what delta G is at non-standard conditions. And we want to know what Q is. So we can rearrange that equation this time in order to solve for Q. When we do that, we see that ln of Q is equal to delta G at non-standard conditions, which is what we were given, minus delta G at standard conditions, which is what we solved for in part A, divided by RT. So to isolate Q on the left side, we need to raise each side of the equation to the e to the power of whatever is on that side of the equation. And so when we do that, we see that Q equals e to the power of delta G at non-standard conditions, which is given as negative 2.50 kilojoules per mole, but we need to convert this into joules per mole by multiplying by 1,000, so that when we subtract delta G at standard conditions from part A, which again is 1.67 times 10 to the third, we can subtract that same unit of joules per mole. And then we divide by RT, which are the same values as we've used before, 8.314 joules per mole times Kelvin, times that temperature of 298 Kelvin. And now when we solve for Q, we should get the unitless answer of 0.19.